We will now look at Quicksort. Quicksort has been around a while. It was developed by Sir Tony Hoare in 1960, and it is a recursive. It's a recursive algorithm. Initially, the array is split into two subarrays. That should sound familiar because that is what happens in merge sort. Except that we don't just split the array into two equal halves in this case. We will pick an item called the pivot or the bound. Pivot is the more common term, at least in U.S. books, textbooks, and so we will pick that pivot, and then we will move array items around to place them with respect to the pivot. So the things that are smaller than the pivot will end up to its left. If you think of the array as having a left and a right, and then the things that are greater than the pivot will end up to its right. So this process will be repeated then on the two subarrays, the one to the left and the one to the right. So the calls are recursive, and so we, just like in merge sort, when we get all the way down to where we only have one element, then one element by itself is sorted, and the recursion unwinds at that point. So this is a recursive function, and basically this consists of two operations. Number one is to choose the pivot, and then the second part is to actually partition the array around the pivot. So choosing the pivot is non-trivial, and so the goal here is to try to have two subarrays that are roughly the same size, but without actually just counting the number and splitting them in two. So here are a few ways that we can pick the pivot. We will use the top one, which is the value in the middle index of the array. Okay, so we will use this for simplicity, even though this is known to be a bad way to pick the pivot. The way to think about this is you can write your own pick the pivot function, and it returns some index, and then from then on you can execute the array. You can execute the algorithm without issues. So you can place all of your complexity for picking the pivot inside that function. Here we will certainly we will just look at the two bounds, the left and the right edge of the subarray, and we will just pick the middle element. Another way to pick the pivot is to look at the first, middle, and last elements in the array. So for instance, if I had a 10 element array, I might look at element 0 and then element either 4 or 5 and then element 9, okay? And then take the median, so the value that falls in the middle out of those three. Another way is to actually just pick three random indices and to look at those and to pick the median value out of those indices. So it turns out that picking a good pivot helps the algorithm, but picking a poor pivot can actually degrade this algorithm, which is an n log n algorithm, down to n squared behavior. So we continue the process until the subarrays are down to one element again, which one element by itself is sorted, and then the recursion unwinds and then sorts the next sublist that needs to be sorted. I will show you some code here in a second, and then we will go over an example to clarify all of this. So the one thing I'll say here is that if you look at multiple books on algorithms and data structures, you will find multiple variations of what I will demonstrate. But the bottom line is that the behavior is basically the same, and it's basically what was come up with some 60 years ago. So if we take a look at this example, and we will work through this entire example, the boxes that you see on the example are the selections for the pivot. So you notice that 60 is picked as our first pivot, and it's actually a pretty good pivot. It's almost halfway through the list, okay? And then when we are through with that pass, everything that is less than 60 in the array will end up to its left. Now, it's not yet sorted, but everything is now on that side, and everything that is greater than 60 is off to its right. Okay, the second pivot that's picked here is the 6, because we do a call on the left side of 60. So it's the 6, and the 6 is a terrible pivot because it's actually the lowest number in that sublist. The sublist being everything to the left of 60. So 6, 42, 57, and 48. The 6 is the worst pivot I could possibly pick in this case, and it doesn't move the process forward at all. I mean, all we do is we actually lock it into place. But there is no splitting going on, and there's no moving of data. Okay, we then pick the 57, we pick the 48, and we sort, and then get down to the 42. The 42 by itself is already sorted. So once the list is down to 1, it's already sorted. So we unwind all the way back to the top. And now we've sorted the left side of 60. So now we call quicksort on the right side of 60. And we begin the whole process again by picking a pivot, by sorting. So in this case, we pick the pivot 73. Everything that's less than 73 is on its left. Everything that's greater than 73 we place on its right. Then we call quicksort on the left side. Well, that's a single element, so that's already sorted. And we call it on the right side and pick some additional pivots all the way until we get down to 1 element. So again, when we get down to this bottom line here, you see that the array is fully sorted. And this algorithm takes a while to go through, but we will go through an entire example to show you how we get from the list at the top to the list down at the bottom that is sorted. Here is a quicksort implementation. This is from your textbook, and I've added some notes here in blue to link this code to the example that I'll go over. So you see that there are some calculations done on some indices here. So the lower index is called lower, and it's 1 to the right of the first element. So what comes into this function is the actual data. This is a template. It's a function template. So it's the data array and then 2 indices. Okay, the first index and the last index. So initially, these 2 will be the entire array. This will be the first element and the last element, but in subsequent recursive calls, this will be a subarray. So for instance, first may have the value 5, and 7, and last may have the value 7. And in that case, we're sorting a 3 element subarray. So again, lower is 1 to the right of first, and upper is the last element. We swap the value that we pick as the pivot, which is first plus last over 2. We swap that with the first position, okay? So I will call that swapping pivot and first. And in this case, this algorithm calls it bound. I don't really like that term. It's not as common as pivot. So you will see the word pivot in the example that I go over. But in essence, the pivot then has been swapped into the first location and is the data at the first location. We then go into this while loop as long as lower is less than or equal to upper. So that means as long as we have at least something to sort. And the key here, so when lower is greater than upper, or upper is less than lower, that's when this while loop will terminate. Okay, the lower bound I will call I in my example, mainly so that it doesn't, so that there aren't too many characters on the screen, and I have too many words there. So I will call lower, the lower index, I will call that I, and you notice that lower moves to the right. It gets incremented. Okay, the upper index, I will call that J in the example, and that index gets bumped down. Okay, so that is an index that is decremented. And when these two stop, so you notice that both of these are in individual while statements. When these two stop, we will actually hit this line of code. And then if lower is less than upper, we will swap the values at lower and upper, at those indices. We will swap the values at those indices. Otherwise, we will just increment lower. And again, that gives us the chance then to come back to the loop and to the top of the loop and actually exit when lower is no longer less than or equal to upper. When this while loop terminates, we have in essence locked in the pivot. And we do that by swapping the pivot with upper. Okay, and in my example, it'll be, so you see that first here is what he calls bound, so that's the pivot. And so we're swapping the first and upper. I will call that swapping pivot and J. Okay, and then we call the function recursively on the left side. So you notice that we came in with first to last. We will now call it from first to upper -1 because upper is where the pivot ended up. Okay, so this is the stuff to the left of the pivot. And if there's, again, if we meet this if statement, we will call quicksort then recursively on the right side. Okay, so that is the algorithm, and hopefully when we go over it, you will then be able to come back to this particular slide and walk through in your mind how we did it. Unfortunately, it's a fairly busy slide, and I can't also paste this algorithm with it. So let's walk through a complete example. So this is the array that is mentioned in the slide, in the previous slide. The data items are in the exact order. This is an array of 10 elements. The bolded values are the indices to this array, so they go from 0 to 9. There are a total of 10 elements. And you'll recall that we said we will pick the pivot by adding first to last and then dividing by 2, integer division. Okay, so let's do that, and we will underline the pivot when we do this. Okay, so first is 0, and last index is 9. We sum those and divide by 2, integer division, we will get the index 4, okay, which makes our pivot 60. The next thing we will do is swap the pivot with the first location, okay? And so in other words, we will not always put it in location 0. We will put it in the first location of the array that we're sorting. And currently we're sorting from 0 all the way to 9. So we put it in the first location. So you notice that I just swapped the 72 and the 60 and I bolded those. So whenever there are data moves, I will ensure that those values are bolded. Okay? So we're now ready to start walking through the array with I and J, which he calls lower and upper in the slide. Okay, in the slide that shows the code. So we will always set I, i.e. lower, to first plus 1. Okay, and then we set J to the last value. Okay. The idea is that I will travel to the right until it finds a value greater than or equal to the pivot. J will travel to the left until it finds a value that is less than or equal to the pivot. Okay, so then I stops if the value is greater than or equal to the pivot. So I starts here. 57 is not greater than or equal to 60, but 88 is. So that's why I is at index 3. Okay, so I stops here. J starts marching to the left and it's looking for less than or equal to the pivot. Well, 85 is not less than or equal to 60, which is our pivot and is in blue. And so it gets decremented, but 48 is less than or equal to 60, so J stops. So this is those two while statements inside that while loop. Okay, when this happens, since I is less than J, I is at 3, J is at 8, so I is less than J, we will swap the values at I and J. So we will take this 88 and this 48 and we will swap them, giving us the picture here with the bolded numbers, okay? And I remains at this location and J remains at this location. And now we will continue to march I to the right and march J to the left. I will continue to march to the right and will look for a value that is greater than or equal to the pivot. And 72 meets that criteria. J will move to the left and look for a value that is less than or equal to the pivot. Again, the pivot is 60 here. So J moves here. 73 is not less than or equal to 60. 83 is not less than or equal to 60, but 42 is less than or equal to 60. So both of these indices stop. And since I is less than J, we swap what we had at those two indices. So we had 72 at index 4 and 42 at index 5. We will swap those two and the indices remain where they are. Okay? And so we must continue. So we're still inside the big while loop. And so now again, I sweeps to the right looking for greater than or equal to the pivot. The pivot is still 60. I find 72 and stops here at index 5. J moves to the left. It's looking for less than or equal to the pivot. It finds 42 and it stops. In this case, J is less than I. So we swap the values at pivot and J, and the pivot, number 60, is now in its final location in the array. It just so happens that that coincides with where it was originally, but the pivot is now locked in. Okay, so once again, why did that happen? Because when these two indices stopped, J was less than I, so we swapped the value that was at J, which here is J, which was 42. with the value at the pivot, with the value at the with the pivot, which is stored at the first location. Okay, so we swap the 42 and the 60, and now the 60 is locked in. And you'll notice I've got some notes here telling us kind of how to do this. Once I show you green, it means that that is the final location for that particular value. Okay, if we recall the algorithm now, we just kicked out of that while loop. So we swap pivot and J, and we must call recursively on the left side. Okay, so a call will be made to sort, quick sort on the left side of 60, and that's what this signifies, Q sort on the left of 60. So that'll be how this is depicted. What's the pivot in this case? Well, the list goes from element 0 all the way to element 3. Okay, those are the only things that are to the left of 60. We add 0 and 3, integer divide by 2, that gives us 1, and that's our pivot, and that's why this 6 is underlined. And then we swap the pivot and the first location. So we swap the value that's at pivot index with the value at the first location. So the 6 is here. It is shown in bold to indicate that it is the current pivot. So where does I and J, where does I go and where does J go? Well, I always goes 1 to the right of the pivot. J is always at the end. Okay, so that looks like this. And again, I will start marching to the right, looking for greater than or equal to the pivot. J will march to the left and look for less than or equal to the pivot. In this case, what happens is I will stop at 42 because it's greater than or equal to 6, which is the pivot, but J moves actually all the way into the pivot. And now, since J is less than I, like we had up here, J was less than I, we swap the values at pivot and J. Well, we swap 6 with itself, but that has the effect of locking in the 6. Okay, so this is an example of picking the worst pivot we could have possibly picked because it did not split the list really in half. Okay, so the way that the code works, we're inside that instance of the function. We will try to call it on the left side, but you remember there's an if statement that checks if there's anything on the left side, and so there isn't. So then we will call quicksort on everything that's to the right of 6, and that's what's shown here. Quicksort to the right of 6. Well, what is that list? That's the list that goes from here, from index 1 all the way to index 3. It's this list, okay? And so we must do the same thing. We take the first index, which is 1, and then we take the last index, which is 3, and we divide by 2. That gives us index 2, and you notice that 57 is the pivot in this case. It's highlighted. So what do? We swap the pivot with the first item in the list that's being sorted, which is just these 3 items. Okay, so swap 57 and 42. Where do we set up I? I goes immediately 1 to the right of the pivot. Where's J? J is always the last item in the list that's being sorted. Okay, and that looks like this. Okay, and I marches to the right and tries to find greater than or equal to the pivot, 57 in this case. J marches to the left and tries to find less than or equal to the pivot. So in this case, I will go through the side of the array. Okay, basically will exceed the size of the array. J will stay put, and that looks like this. Okay, so you notice that I've just put this I in here. It's not it's not this value. It's just showing that it's gone past the boundary of the list, which ends at 48. But J stayed put because 48 is less than 57. Once again, since J is less than I, we swap the value at the pivot with the value at J. In this case, we swap, here's the value at J is the 48. Here's the value at the pivot. So we swap the 48 and the 57, giving us this particular configuration. And the 57, which was our pivot way back here, is now locked in. So the recipe is always the same. Once we pick a pivot, we know we're going to be locking that specific value into its place. Okay, so our pivot was 57, so we've got to call sort to the left. Okay, so we always go to the left first. We've got to call quicksort recursively with this sublist made up of 2 items. What does that look like? That's an item, that's a subarray that begins at element 1 and goes to element 2. So, okay, so we call quicksort to the left of 57. Add 1 plus 2, divide by 2. Integer division of 3 by 2 is 1. So 48 is our pivot. Okay, swap the pivot with first. Well, 48 is still the pivot. Okay, it's swapped with itself. Set up I and J. Well, I is always 1 to the right of the pivot. J is always at the last. So in this case, they're both at the same location. I sweeps to the right, looking for greater than or equal to the pivot, which is 48 in this case. J sweeps to the left, looking for less than or equal to the pivot. Well, J is already at less than or equal to the pivot, so it holds. I goes off the side of the list, and since J is less than I, then we swap the pivot and J. J is at location 2, the pivot is at 1, so that means swap the 42 and the 48, and that looks like this. And you notice that since it was our 48 that was the pivot, it's now locked in place, it's in green. And we now have to call on the left side to sort the sublist on the left side. When we do, that is a sublist of length 1, and it's already sorted. Okay, so the recursion unwinds back to this point and unwinds really. There's nothing to call on the right side of 48. There's nothing to call on the right side of 57 because we're only dealing with this sublist here. And so the recursion unwinds basically all the way back to the top where we first called the left hand side. Okay, so you notice that the entire left hand side is from the pivot. From that initial pivot, everything to the left is now in place. Okay, so we locked in the pivot, and then we called on the left on the left subarray, the subarray to the left of the pivot. So everything now is locked in. So what do we do next? Okay, we call quicksort to the right of 60. That means coming way back here. The recursion unwinds, okay, all the way to back here, and we call it on the right side of 60. Okay, and what is that sublist? That's the sublist from index 5 to index 9. So 5 plus 9 div 2 is 7. So 7 holds value 73, and that's our pivot. We underline the pivot, and then we swap the pivot with the first item. What is the first item? It's the 72 because we're sorting these 5 numbers. Okay, so swap the 73, the pivot, with the value 72. Okay, where does I go? I is always 1 to the right of the first location, which is what holds the pivot. J is always the last item. I sweeps to the right, looking for greater than or equal to the pivot, so I stays put because 83 is greater than or equal to 73. J is looking for less than or equal to the pivot, so it sweeps all the way to the 72. In this case, these two indices haven't crossed yet, i.e. J is not less than I. Okay, so since I is less than J, we will swap the values at I and J, meaning we will swap the 83 and the 72, and that looks like this. And the indices remain where they are. So again, I is going to continue to sweep to the right, looking for greater than or equal to 73. J is going to sweep to the left, looking for less than or equal to 73. So this is what happens then. I finds 83 because it's greater than or equal to 73. J, moving to the left, finds 72 because it is less than or equal to 73. And since J is less than I, we swap the pivot, 73, with J, 72. Okay, giving us this picture. Okay, and 73 was our pivot selected way back here. It is now locked into its final place. Okay, all right, we're now just going to transfer everything to the next page. Okay, so this is just the last operation that we did on the previous page. So where are we? Well, we just placed this pivot, so we must now call it on the left-hand side. What is the left-hand side? It is simply this value. Okay, it is simply the 72. It doesn't go all the way back to the 6 because this instance of the function was called with 5 to 9. Okay, so calling it on the left hand of 73. So we call quicksort on the left of 73. It's a single item, and a single item is sorted, which means we have now locked that value in. And now we will call quicksort on the right side of 73. Okay, and we notice that when we call it on the right side of 73, the list goes from index 7 all the way to index 9. 7 plus 9 div 2 is 8. So at index 8, we find the value 88, and that's the pivot. Swap the pivot with the first element in the list. Where is the first element? It's the 83. So we'll swap the 83 and the 88. Okay, and we'll recall that the 88 is the pivot in this case. Where's I? I is always 1 to the right of the first location, i.e. 1 to the right of the pivot. So I is at 83. Where is J? J is always last, at the last location. So J has value 9 because it's an index. I has value 8 because it's an index. Okay, and I will sweep to the right. Okay, and J will sweep to the left. I is looking for greater than or equal to 88. J is looking for less than or equal to 88. Well, J stays put. Okay, J stays in place because 85 is less than or equal to 88. But I goes off the side of the array. Okay, and in this case, J is less than I. So we swap the pivot, which is 88, with the element at J, which is 85. So we swap the 88 and the 85. And since the 88 was our pivot, it is now locked into place. What must we do now? We must call quicksort on the left-hand side of 88. So we call quicksort on the left side of 88. What is the size? What is this list? What are the extents of this list? Well, it goes from index 7 to index 8. So pick the pivot. The pivot index is 7 plus the 8, div 2. That yields the integer division. That gives us a 7, which means the 85 is the pivot. Okay? Swap the pivot with first. That's basically swapping the pivot with itself. Okay, and so we have this picture now. Okay, now we have to set up I and J. I will be always 1 to the right of the pivot. J is always last, meaning they're at the same location. I sweeps to the right, looking for greater than or equal to the pivot. Notice this 88 is not part of this list. I'm only sorting these two values. So I is going to go off the side of the array. J is already at a value less than or equal to 85, so J stays in place. So that looks like this. And since J is less than I, we will swap the location, the value at J with the value at the pivot. So we will swap the 83 with the 85, giving us this picture. And at this point, again, it was the 85 that was our pivot. We just locked that in. So we now call Quicksort on the left-hand side. Okay, so calling it on the left-hand side of 85. That is a one item list. So it is sorted and locked into place, and the entire thing is fully sorted. If we look at it, 6, 42, 48, 57, 60, 72, 73, 83, 85, and 88. It's an ascending order sort, and that's how you do it with Quicksort.